Welcome everybody to the Johnson Matthey Platinum Group Metals Conference, Critical to the Future of Sustainable Technology. So what is the role of PGMs in the future technologies, or those technologies that are going to allow us to have a beautiful, sustainable and successful future as human beings on our wonderful planet? My name is Dr. Sarah Gordon. Now, before we get started, or basically the bit that you have all been waiting for, because of course this is a conference, and Emma, I'm going to invite you to maybe say some words against this particular slide, because of course this is a Johnson Matthey conference. There is a little bit of a legal disclaimer we need to flash up at the beginning in front of you. We will put this into chat as well if any of you want to read this in detail. So our second presenter of this third session within our conference is the phenomenal Lenka. Now Lenka's going to start sharing her slides. I can see she's off mute already.
Yes.
Emma gave a fantastic opening spiel with regards to Lenka, but I'd invite everyone, please put your hands together and I will pass across right now. Thank you very much. Lenka, over to yourself.
Yeah, thank you very much for the nice introduction. I would like to thank also Emma for the invitation. It's a real pleasure to be here today. From the city of Grenoble, which suffers from some heat wave currently. So you see my fan working. I hope that it does not disturb the sound too much. So my presentation will be about using the SCA for process evaluation, and I will focus on the case study of platinum closed loop recycling for the PEM fuel cells. My name is Lenka Svecova, as you mentioned. I'm from the LabME lab, which is an electrochemistry lab here in Grenoble, in the southeast France, somewhere between Lyon and Geneva. Before going inside our own work, I would like to introduce or explain or recall the principle of a proton exchange membrane fuel cells in order to better explain for the people who are not familiar with. So what is PEM fuel cell? It's an electrochemical device that will use hydrogen and oxygen to produce electricity, but could produce also some heat and some water. Both gas flows do not react directly. You have at first hydrogen that is oxidized at the anodic side of the fuel cell, producing protons that will travel through the proton exchange membrane to the cathode side, where it will participate in the oxygen reduction, producing water, and as I've explained, some electrons that will travel through the external circuit and supply some energy. So both anodic and cathodic half reactions are catalyzed by platinum nanoparticles that are supported on carbon particles, and you have also the ionomer, so the proton exchanging polymer. And all of the three components ensures what we call the triple point. So that's exactly where that reaction happens. In the heart of the fuel cell is what we call the membrane electrodes assembly, an MEA. So you have in the middle the proton exchanging membrane, that resembles a little bit to Teflon, but has also some sulfonate functional groups. Then you have two electrodes with the platinum nanoparticles, carbon black and naphthalene. And then you have two gas diffusion layers, so that helps to diffuse better the hydrogen and oxygen gases. And you can have also some a gasket. So these MEAs will be then assembled together, so stacked to produce a stack, which will be inside, for example, hydrogen-propelled car. The cost and the environmental impact of the platinum are often pointed out. So the platinum, but also the naphthalene, will significantly affect the fuel cell cost. Platinum is also considered as a burden from the environmental point of view, as you've seen in Tanya's presentation. As you may know, it's considered as critical raw material by the European Union, and so it's primordial to reduce these joint effects, and several strategies have been proposed, like decreasing the platinum quantity. So we are talking about platinum loading, so the milligrams of platinum per square centimeter of the MEA. Increasing the catalyst durability. There are a lot of works, a lot of people around the planet working in this. Using platinum alloys, for example, you can alloy platinum with cobalt or nickel, or even use non-PGM catalysts, but they do not work perfectly, or doing the recycling. So closed loop recycling, producing catalysts from recycled platinum might also be a way to decrease these joint effects. And I will try to explain you whether there's some environmental soundness in this, and what benefits of environmental credits we can create by recycling. So when we started to work on this topic, we started to work on the MEA level, so very small scale. We wanted to see whether we can recycle the platinum, and whether there will be some environmental benefits related to the platinum recycling. So we've compared two scenarios that you can see here on the left side of the slide. So we did not include the use of the fuel cell in a car for reasons that I will explain later on. So we have considered the MEA production, and then in the reference scenario, MEA incineration, so no recycling. And then we have our recycling scenario. When we will recycle some parts of the MEA, we will incinerate the membrane and the GDLs, so the gas diffusion layers, and we've developed 4 different alternatives for platinum hydrometallurgical recycling. And you have here some data on all the inflows by emissions from our process. So this is how we modeled our production. So primarily platinum coming in, then transformed into the salt used to produce then the catalysts. And we've also modeled the other components like the naphtha and the PT for gasket, the GDS, so with carbon fibers, etc. And then we recycle them. So we will use some chemical products, we will use some electricity, we will use solvents, ion exchange resins, things like this. And finally, we will produce a salt. So our functional unit was manufacturing and recycling 1 MEA of 25 square centimeters of active surface area. And we've compared 2 different scenarios, incineration and recycling. Particular thing, as you may know, 100% efficiency is not achievable. You will always lose a little bit of matter. So if we have lost a little bit of platinum on the way of the recycling, we've supplemented it with some primary platinum. So at the end, we will have a mix of primary and recycled platinum. So what we wanted to see at first, what are the environmental burdens of the MEA production, and you can see here several, I think 10 or 11 different environmental impact categories that have been assessed. And we can see that on the MEA level, the platinum dominates the impacts of the production stage for nearly all the impact categories. However, naphtha, so the membrane, will score extremely high in ozone depletion layer category, where it's nearly the only contributor, and will score high also in the global warming potential, so in the CO2 equivalents. What about the chemistry of our recycling process? So we've developed a process that can be run and operated at 25 degrees, so no heating. So we've studied 2 different alternatives of leaching, so dissolution of platinum. Then we've compared the solvent, so extraction and back extraction process with ion exchange, so absorption and desorption, followed by precipitation, and we've obtained this platinum and ammonium salt. So this was the feasibility part, and then we've done some optimization. So the optimization was focused on produce a highly concentrated solution, not on the efficiency part. So we've done some multi-stage cross-current configuration with several stages in order to optimize our separation process. And what we can see when we compare here the scenario number 1, so without recycling, with the scenario number 2, including recycling, is that you have a decrease of impacts, as Tanya already explained previously. So recycling of platinum leads to significant reduction of impacts, except for the ozone depletion potential category, which is nafine sensitive, and then global warming potential, where both platinum and which is also platinum, but also nafine sensitive. So the decrease is less important in this category if you recycle only the platinum. And then the idea was we are working with a lot of people doing electrocatalysis in the lab, working really in the durability of the catalyst, in the synthesis of the catalyst. So the idea was, hey, can we collaborate with these people, and can we synthesize in a closed loop manner the catalyst, and can we test it then in fuel cells? And that's what we've done later on. So this time we were not working only on the platinum-based catalyst, but on the platinum alloy containing also the cobalt. And we've adapted our process to the selective separation of cobalt and platinum, with a still objective producing highly concentrated platinum solution. And what you can see here when you combine several steps, although they are very efficient each time, so to get the global efficiency, you multiply all of them, and then the global efficiency, unfortunately, it's not as high as you would like to have. So we've lost a bit of platinum, something between 15 and 20%. This platinum can be naturally recovered later on, but it will necessitate more steps, and at the end you will have more diluted solutions. So we did not do this. And we just produced here not a salt but alkaline platinum solution. And when you compare both alternatives, so based on solvent extraction and ion exchange resin, you can see that solvent extraction is much more impacting, with the exception of ozone depletion layer potential, where the resin alternative scored much more high. Then what we've done is that we've used directly this alkaline platinum solution for the catalyst synthesis. So you have here the experimental conditions, and we've seen that we can produce a catalyst. So we can see it here on the TEM images that resembles visually a lot to the reference one used in the literature. We have exactly the same nano-sized platinum particles that are obtained when we use the ion exchange resin alternative. However, for the solvent one, we have much bigger particles that are synthesized, and this was explained by the presence of traces of solvent. So with this kind of surfactant effect that it's harmful for the nanoparticles formation. So we've only continued with this resin-based recycled platinum, and it behaved electrochemically exactly in the same manner as the reference catalyst, which was very, very good news, very good result. And when we then compare when we analyze the impacts just of the synthesis part, we see that the major contribution comes from the primary platinum that we have to add to the system to mitigate the losses that we had in the process. And when you compare the recycling process impacts and the polyol synthesis impacts, they are of the same order of magnitude or even a little bit higher than the recycling process impacts. So indeed, the recycling process does not impact a lot and brings a lot of benefits. And when we have, when we gather all the results together using this functional unit based on the closed loop recycling, so you have both the production and the recycling process, you will still mention here or see here the obvious, very obvious impact of the primary platinum that we supplemented to mitigate our losses. However, in the global warming potential and in the ozone depletion potential, you will still see the very big contribution of the naphtha. So not only the platinum needs to be recycled with mitigation of the losses, but also the naphtha should be recycled. So this is something we are trying to develop in my lab. And then I wanted to compare our data with some other literature data. And the question was whether the platinum impacts are still visible even at the stack, the PEMFC stack level. And the answer is yes. The results comes from a very recent article. You have here the reference. So platinum, even in a stack level, still scores high. Except the eutrophication potential. So there's still a major contribution of platinum to studied impacts even at the stack level for the production stage. However, the authors of this article has confirmed that the recycling and the decrease of the loading can significantly decrease the production impact of the PEMFC stack. As you can see here, so this is the reference scenario with approximately 0.5 milligrams of platinum per square centimeter. So if you recycle only this platinum, you will have already 30% of an environmental benefits. If you go also into the decrease of the platinum loading, then you decrease further on the impacts. And if you combine both decreasing the loading and efficient recycling, you can let's say up to 50% of environmental impacts, which is a very nice result. But whatever about the hydrogen propelled car? So these are some data that I've taken from this publication. So they compared two different scenarios, 2010 and 2020 based scenario to an internal combustion engine propelled vehicle scenario. And what you can see that for the classical car, the majority of carbon footprint is associated to exhaust emissions, so the use phase. When you switch to hydrogen propelled vehicle, so you have a pollution transfer, which goes from the use phase to the production stage and is associated to hydrogen production. So the red color you can see here is associated to fuel production, so to hydrogen production. So depending on the hydrogen production pathway, the hydrogen propelled vehicle might or might not be interesting from the environmental point of view. So you can see that, for example, if you use natural gas reforming, it scores a little bit higher than the petrol propelled vehicle. If you use coal and coal gasification reforming, you will score even higher. If you are doing electrolysis of water using European electricity mix, you nearly double the impact. But if you have some PV panels that produce your electricity and then you do electrolysis and produce hydrogen in this way, you will see that the hydrogen propelled car scores better. You will find same trends when you have a look to other impacts like acidification. And these kind of results are confirmed by other studies. For example, this one where they compared hydrogen vehicles and battery propelled vehicles with the petrol propelled vehicle. So you still have the pollution transfer from the exhaustion gas, so the use phase, to the electricity or hydrogen production. And depending how you produce your electricity, there will be some environmental benefit or not. But the platinum is no more visible at the car level. So what are the take-home messages? So there's some cost associated to the use of platinum at the MEA level and the stack level. There are non-negligible environmental impacts of the production stage due to the use of platinum, but also other materials. In the former generations of fuel cells, we used the bipolar plates made from graphite, so they scored also high. Today they are more steel-based, so there's less impacts associated to the bipolar plates. But the MEA contributes at least to 50% of impacts in all study categories, with significant contribution of platinum. At the fuel cell vehicle level, there are still some important contribution coming from platinum from the production stage and of the vehicle, and the carbon fibers that will be used for the hydrogen tank. However, when you take into the account also the fuel, as we've seen, there will be major impacts of the hydrogen. So how to reduce both cost and environmental impacts of the PEM fuel cell technology? So you should increase the durability of your catalyst, decrease the platinum loading. If possible, try to substitute the platinum, but please be careful with this, because if you put the nickel in your platinum alloy, you might have some pollution transfer with a lot of acidification coming in. And naturally, we've seen in my presentation and Tanya's presentation that the recycling is the right way to decrease the environmental impacts, at least at the MEA and stack level. Regarding the vehicles, there is really a very significant contribution of the hydrogen production pathway. So the fuel cell vehicle can decrease the greenhouse gases emissions by 50% only and only if the hydrogen is produced from renewable electricity. And what we can also learn from the literature, the results, the LC results are very dependent on the parameter of the study and the study's objectives. So I would like to finish by the acknowledgement to all the people that accompanied me on the travel through the LCA and platinum recycling. And you have here some of the articles that we've published on this topic. And thank you very much for your attention. This picture, this photo is for Sarah. You have some beautiful mountains here in Grenoble. So I thank you very much for your attention, and I hope that we will have an occasion to meet here. Thank you very much.
Brilliant. Thank you so much, Lenka. Round of applause from all of us. That was great, especially I'm loving, we've got Grenoble putting its mountains in there. Yesterday we had some mountains in Italy being put out there. So there's a secret competition that's going on behind the scenes with regards to who has the most exciting mountains. Thank you so much for that, Lenka. That was so interesting, and a brilliant insight into, actually, from a very practical and fact-based perspective, where are there wins in terms of recycling and in improving our environmental impact on our planet. Now, Emma, I know that you had a question that you wanted to ask. I'll pass over to you straight away.
Well, I know, Lenka addressed it to some extent in these platinum losses within the process. How much overall platinum were you expecting to lose? Because we don't lose platinum in the industry.
Yeah.
We just
in fact,
yeah,
when I announced to Emma that we were losing like 15 or 20% of platinum. She was quite shocked. So that's what I wanted to explain. We wanted to produce very high concentrated solution. So we did not want to focus on 100% platinum. 100% is not possible, but I think if you minimize the number of steps, so you will minimize also the losses. I think we developed another pathway that we are trying just to publish now, so I cannot give you some details, but we have only 2 steps there, the leaching and then the synthesis. So you can have something like 95%, I think. You can, depending whether your focus will be to recover the maximum from platinum on having a very concentrated solution, you will not get exactly the same thing. And with the platinum, the thing is also to collect all your spent fuel cells. So this will be the very first step. If you collect them, then you can efficiently recycle them. And then the problem is, if you want both platinum and then the naphtha membrane, then during the operation of the fuel cell, there you have some aging, some dissolution, and some platinum gets stuck inside the membrane. So it's no more accessible for the leaching solution. So I think honestly that's something like 95%, 98 is possible, feasible, let's say. Possible, I don't know.
I mean, it's really nice that you have an appreciation that some people, let's say, that the materials and the constructs change from the beginning of life to end of life. And of course, everything becomes more difficult during the lifetime because of that degradation, because of migration of not just platinum, but some of the other metals start wandering around and end up in places where we really don't want them. But the great thing about what you're doing is that, and I'm hoping that all the researchers and all of the institutes who are listening are making notes and saying, right, I need to focus on improving this, because really, if we have a technology problem, we also, as a world, have the brain power to be able to solve it. And but only with a life cycle assessment and the detail that you've been able to put into this, are people able to say, actually, I need to concentrate on the carbon fibers which were in the hydrogen tank. That's probably not the first thing that you think about when you're talking about a fuel cell. So it's an incredibly helpful, almost signposting exercise to people to say, look at this, this is what's important. Don't get misled by just focusing on only the platinum. The MEA is in there. The MEA is valuable and important. So thank you so much for talking about that. It's really important for everyone to understand the challenges that are facing us.
Thank you. Welcome.
So good news. It's not that we're just losing it. So Emma can breathe again and feel slightly more relaxed in the world. Lenka, what we're going to do is we're going to go straight into our next presentation. There are some questions for you in the Q&A, but also, of course, we'll be coming back for a much bigger discussion very shortly. So everybody, please put your hands together to show our appreciation for the phenomenal Lenka. Thank you very much. Brilliant.